In this DeBacco University video, I'm going to go through a breakdown of the atomic theory of John Dalton. All right, let's get into the atomic theory of John Dalton here. Now, with any scientist, you want to have an idea of the context of the development of their theory, what was kind of going around at that time, because we're talking lived in the 1766 to 1844 timeframe, and this theory came out around 1803 to 1808. And this is during a time when chemistry was transitioning to more of a rigorous science there. Laws of chemistry, laws of conservation of mass, laws of definite proportion, empirical laws suggesting matter had a constant particulate nature. These are all kind of what's going around at the time. There's also gas studies being done, and this kind of led him to ponder the nature of matter at a microscopic level. Again, we're talking very small here at the atomic level. You wonder why gases mixed and behaved in predictable manners. Inspiration from earlier thinkers. Dalton's approach was distinctive. It was quantitative and testable, unlike speculative philosophy. So it's kind of going on at the time that led him to develop his theory. And his theory, typically, as we think about it now, we think about it as what's called the billiard ball model. So you have like a pool table, a cue ball here, that atoms are indivisible and indestructible. Again, here's his concept. He viewed atoms as a solid, indivisible spheres like tiny billiard balls. He believed they were the smallest possible units of matter, incapable of being split or destroyed. And of course, we've gone and progressed from there, but again, we're just laying the foundation here. His theory was that they were small, indivisible atoms, essentially, that couldn't be divided and were basically all in solid form. So again, if we look at his theory in a little bit more detail here, unique atoms for each element. Each element had its own type of atom, characterized by a specific mass and properties. The chemical reactions as rearrangements. Dalton proposed that chemical reactions involve the rearrangement of atoms, not their creation or their destruction. So you kind of believe that, all right, they stick together, they fall apart, they rearrange. So that, again, that idea still holds true today. So we can see that even way back then, still some connections to the modern day theory. Looking at some other ideas that it came up with, again, the fixed ratios in compounds, atoms combine in simple whole number ratios to form compounds. This supported the law of definite proportions and provided a way to predict compounds' compositions. Also, the law of multiple proportions, where Dalton observes that when two elements form multiple compounds, the masses of one element combined with a fixed mass of others are in small whole number ratios. So we can still, again, apply this today. Still look at the law of multiple proportions, how things are combining, how we can track certain things in the reactants versus the products, how things can rearrange, but yet the masses remain the same on both sides, as again, assuming they're a closed system. So his different postulates here. So we've got kind of one part here to kind of break them down, because he had quite a few postulates. All matter is composed of atoms. So those atoms are tiny indivisible particles. They're the smallest units of an element that retain its properties. Another postulate that he came up with was atoms of a given element are identical. All atoms of a specific element are the same mass and size and properties. Atoms of different elements have different properties. We see that now with our more modern day periodic table. We know our different properties for some of our different elements. Atoms cannot be created or destroyed in chemical reactions. Atoms are rearranged, but their total number and type remain consistent. And remember, this is the law of the conservation of mass. Now, we also had two other ones. We said atoms combine in simple whole number ratios. So chemical compounds form when atoms of different elements combine in fixed simple ratios. For example, H2O, or water, has 2 hydrogen atoms and 1 oxygen. And then atoms are rearranged in chemical reactions. So we take those chemical reactions, they can involve combinations, separations, rearrangement of those atoms, but the atoms themselves remain unchanged. So there's these 5 key postulates here. How does this kind of relate to the modern atomic theory? Again, that solid sphere model was John Dalton. The structure of the modern theory does describe atoms as a complex system. Dalton thought they were solid spheres. Divisibility, atoms can be split in nuclear reactions, and Dalton kind of thought they were indestructible, they were solid. The concept of isotopes, modern theory does recognize isotopes. Dalton assumed that they were all solid and unchangeable. Quantum mechanics does explain how electrons facilitate in chemical bonding. Dalton's model really didn't address this particular aspect. He said they combined, but didn't really get into the bonding aspect. And lastly, for conservation, Dalton's idea that the atoms are conserved in chemical reactions does still hold true, and modern theory can kind of take this and transform in nuclear reactions, uranium decaying into lead. So there are some nuances where that could change. However, we're talking 1803 here. So again, this started the progression. As we look at other scientists, we'll see how this solid sphere model gets refined and gets closer to our modern day model.